Welcome to one more video on linear integrated circuits. Here we are again looking into the applications of op-amp. So in this video we are looking at a precision rectifier. So let us have the introduction of a precision rectifier. So we already know what is a rectifier. So rectifier is a circuit used to convert AC signal to DC, and the input levels are more, that is input voltage levels are more. It is in terms of volts, so it can be 1 volt, 5 volt, 10 volt, whatever. So usually we have used input voltage of larger amplitude to rectify an AC signal to a DC signal. If the input amplitude is less than the cut-in voltage or the built-in voltage of the diode, this type of rectifiers will not work. Meaning, we have seen in the working of rectifier, if the input voltage exceeds the cut-in voltage, then diode conducts. So then we had the current flowing in one direction and it was not flowing. And of course, we had different varieties of rectifiers. Suppose if the input voltage amplitude is less than the cut-in voltage, then this type of rectifiers won't work. Next is a rectifier circuit built using diode and an op-amp. So now the combination of a diode and op-amp will be called as super diode. So this is used to rectify the signals of lesser amplitude. Even if the amplitude is less than the cut-in voltage of the built-in voltage of the diode, so we'll use the combination of this diode and an op-amp, which will be now called as a super diode, and this combination of diode and op-amp will be used to rectify signals of lesser amplitude, which is less than the cut-in voltage. Now we shall see the precision rectifier working, that is a half-wave rectifier. Now this rectifies a signal less than cut-in voltage of the diode, that is if the input voltage is even if it is less than 0.1, 0.6 volt. The circuit diagram looks like this now. You can see now the op-amp and the diode. Now the combination of op-amp and diode is now called as a super diode, and a resistor is used to take the output voltage here. Now this circuit is a precision rectifier which will give a half-wave rectified signal. You can see the transfer characteristics of the same is given over here. So let us see the working of this precision rectifier in detail. Now this is what we are looking at: a super diode and a resistor. Transfer characteristics: the output voltage is 0 when it is negative half cycle, when the input voltage is negative. When the input voltage is positive, the output is exactly following the input because the slope is 1. Now we know that the op-amp in the open loop is given by A0 into V plus minus of V minus. So A0 is the open loop gain of the op-amp. Now V plus is the voltage applied to the non-inverting terminal. V minus is the voltage applied to the inverting terminal. Now you can see now the input voltage at V plus is V in, whereas at V minus initially it will be grounded here. Now assume that when this diode is off, there is no current flowing through this resistor R. So the voltage at V0, which is connected to V minus, will be 0 initially. Suppose under this condition, if the input voltage is greater than 0, as you can see now the input voltage is connected to the non-inverting terminal. Whenever that V plus becomes more than V minus, so V minus is initially 0. Suppose if the input voltage slightly goes above 0, even if it is 100 millivolt, 10 millivolt, now because of this A0 gain, so V plus will be more than V minus. Because of this A0 gain and this V plus is more than V minus, we will have the output voltage at this point, that is VA, far greater than VD on. So it will be almost plus VSAT. So the voltage here is plus VSAT, which will be greater than VD on, which will make the diode turn on. Once diode turns on, you can see neglecting this voltage, now this looks like this voltage is fed back to the inverting terminal. Now this looks like a voltage follower. When this looks like a voltage follower, the output exactly follows the input. Now that's what is written here. When the input voltage is greater than 0, the voltage VA, that is output of the op-amp, will be plus VCC, which is certainly more than VD on, which will make the diode on. So when diode is on, we'll have the output voltage equal to input voltage. Now because this acts like a voltage follower. Now assume because this acts like a voltage follower when the diode is on, neglecting this diode drop, the output voltage is equal to input voltage. That's why you can see even for very smaller voltages, very small in terms of even 1 millivolt, the output voltage VA will be plus V sat, anything greater than 0. It need not be greater than cut-in voltage. Even if it is 1 millivolt, 10 millivolt, the V plus will be more than V minus. Whenever this condition comes, VA will be greater than VD on, which will turn on the diode so that output voltage is equal to input. So that's why you are having a slope of 1. Now let us see what happens when the input voltage is less than 0. When the input voltage is less than 0, now we have the condition V plus is less than V minus. So we are supposed to get the output voltage here as minus VCC. Once you have a negative voltage, this diode turns off. So now this VA is minus VCC, which is less than VD on. The diode turns off. When diode turns off, this is output voltage. Now output voltage looks floating now. So we have no connection over here. Now once it is open circuit, the output voltage is connected to this inverting terminal. So inverting terminal is actually the input voltage. Now this output looks floating. So this is a floating voltage here. But when the diode is conducting during the positive half cycle, the output follows the input. Now in this precision rectifier, which is a half-wave rectifier, we have one disadvantage of output floating when the input voltage is negative. So this will be overcome in the modified circuit as it is shown over here. So this is again a precision half-wave rectifier, second type. You can see now. So we are using an op-amp and two diodes now. So you can see now. Let us see how does this will work. So VA is again the voltage at this point, that is VA is given by V plus minus of V minus, which is nothing but A naught of, now V plus is now grounded. The input voltage at inverting terminal is now V in. If the input voltage is greater than 0, whenever the input voltage is greater than 0, so we know that this will be negative. So whenever the input voltage is greater than 0, since it is connected to the inverting terminal, so when the inverting voltage becomes more than the non-inverting voltage, we are supposed to get this as negative. When this is negative, this diode D1 is off. So that's what is written over here in the detail. When Vin is greater than 0, VA is negative. That is, the voltage at this point is negative voltage. So D1 is off. So but D2 is on. So when D2 is on, we are having this voltage coming over here. So this loop is closed. Since we are taking the output voltage over here, which is the voltage drop across resistance R2, since diode D1 is off during the positive half cycle of the input, because this voltage is negative, diode is off. When diode D1 is off, so we're going to get the output voltage 0 over here, meaning for positive half of the input voltage, the output voltage is 0. Now let us consider when the input voltage is negative. When the input voltage is negative, that is less than 0, so this will be now positive over here. When it is positive, this D2 is off. So you can see D2 is off, whereas D1 is on. So the voltage at this point is positive because it is connected to the inverting terminal. When V minus is less than V plus, so we have a plus VCC. This plus VCC will turn on this diode D1. Once D1 turns on, you can see now this will look like a short circuit. Now this is an open circuit. Now you can see this looks like a inverting amplifier. So that's why the output voltage is now given by minus V in multiplied by R2 by R1. So this is the expression for the output voltage of an inverting amplifier, which is nothing but minus V in R2 by R1. Now this slope will be equal to 1 if the value of R2 is equal to R1. If R2 is more than R1, then the slope of this line changes. So actually the slope of the line is given by R2 by R1. If R1 and R2 are same, we won't have any slope of only 1. So in this particular half-wave rectifier, the output is either 0 or ground, 0 or VCC, 0 or the input voltage with respect to gain. So we will never have a condition of output floating. So it is an improved version compared to the previous circuit. In the previous circuit we had the output floating here. Now in this second circuit, the output is neither 0. Of course it will be either 0 or the input voltage multiplied by the gain. But here it's an when the input voltage is positive, output is 0. When the input voltage is negative, output is positive. So that's why it is when input is negative, we have the output voltage minus of Vin, which happens to be the positive voltage. Now let us see how does a precision full wave rectifier conceptually realized. As you can see now, so let us consider A as the input and C as the output. So if you consider this A is the input, which is the sine wave whose amplitude is less than uh, cut in voltage. So okay, let us conceptually assume that during positive half cycle we will make this super diode turn on. Now this is just a conceptual circuit. If this diode turns on during the positive half cycle, so at point C we'll have this waveform. So this A is coming over here at the output because of this diode is D1 is conducting, and the same input voltage is connected to this diode B using an amplifier, inverting amplifier. So at B point, during the positive half cycle of the input voltage, at B point we have a negative voltage, so that's why D2 dB is off. So we'll have the output voltage at C during positive half cycle of the input due to this diode dA. So let us assume this during negative half cycle of the input, because of this inverting amplifier, the voltage at B will be positive. So because B is actually the inversion of the input, now you can see B is actually inverted compared to A. Now we have a positive voltage. So this positive voltage is going to make the diode dB on. Whenever dB is on, now you can see the output voltage follows the input voltage, meaning during positive half cycle also we'll get the output voltage due to this diode dA. During negative half cycle of the input voltage also we get the output voltage in the same direction, that is due to dB. So using an inverting amplifier over here, the output voltage is there both during the positive half cycle of the input voltage and negative half cycle of the input voltage. So this concept can be realized using super diodes and an inverting amplifier. That's what is given here, as you can see here. So this is the input voltage. Now this will represent that super diode which was represented by dA. Now we have this A2 and D2 forming the super diode, and this inverting amplifier and this D1 forming the dB of that conceptual. So this dB is formed due to that found by the inverting amplifier and the diode D1. This is the representation of dA. Now you can see when the input voltage is positive, so this voltage at VE is positive. So because this is a voltage follower, when it is voltage follower, the voltage is positive over here. When it is positive, the D2 turns on. So D2 turns on whenever the input voltage is positive. So this is negative here. So we're going to have the VF as negative voltage. So it is less than VD on. So D1 is off. So D2 will be on, D1 will be off when the input voltage is greater than 0, that is during the positive half cycle. So we'll get the output voltage because of this voltage follower during the positive half cycle. So we get the waveform which is exactly following the input. Whereas during the negative half cycle, this diode D2 is off because VE is negative. When VE is negative for that input voltage negative, D2 is off. You can see D2 is off. Whereas when the input voltage is negative, because of this inverting amplifier, we'll have this the voltage at Vf is now positive. When the voltage at Vf is positive, which is more than the VD1 of this diode D1 transistor, now D1 turns on. When D1 turns on, so we have the input voltage coming at V0 due to this inverting amplifier. So that's why we'll have the output voltage, which is nothing but the inverted version of the input voltage with a gain of R2 by R1. Now here this is going to have a slope of 1, whereas this can have a variable slope of R2 by R1. So this way we can able to get the waveform which is expected over here. So this is due to the voltage follower and this is due to the inverting amplifier. So that's what we are seeing over here. So this is this portion is due to voltage follower and this portion is due to the inverting amplifier. So input voltage greater than 0. So we have the output equal to input. When it is less than 0, output voltage is inversion of the input.